we move on to prove fact 1. Proving fact 1 and fact 2 are the key steps in the proof of the stability theorem. This is where we are going to use the integral Lipschitz conditions to bound error terms. Of the two facts, fact 1 is the easier to prove. We repeat the statement here for ease of reference. The statement of fact 1 involves the definition of the term delta 1 of s times x and the bounding of its norm by 2c epsilon for any vector x that has unit norm. In the definition of delta 1 of s times x, we have three summations. The innermost sum is over index r, which represents different powers of s. It comes from the binomial expansion in equation 20. The middle sum is over index k, which is associated with different filter coefficients hk. It comes from the definition of the graph filter we introduced in equation 19. The outermost sum is over index I, which is associated with the components of the GFT of x. It comes from writing the signal x with the inverse GFT, as we did in equation 25. To begin with the proof of fact 1, we focus first on the innermost sum, the 1 over index r, and notice that the error matrix eigenvalue m sub I is a scalar that can change places with powers of s. We now use again the fact that v sub I is an eigenvector of s to write s to the power of r times vi as lambda I to the power of r times vi. And, likewise, to write s to the power of r plus 1 times vi as the product of lambda I to the power of r plus 1 times vi. When we do that, the innermost sum in 36 reduces to the expression we show in 37, where really all we have done is replace powers of s by powers of lambda I, which we can do because lambda I is the eigenvalue of the matrix S associated with eigenvector v sub I. This substitution produces a remarkable simplification because the sum in 37 involves a term of the form lambda I to the k minus r times lambda I to the r, which equals lambda I to the k, irrespective of the value of r, and a second term of the form lambda I to the k minus r plus 1 times lambda I to the r plus 1, which reduces to lambda I to the power of k irrespectively of r as well. Thus, all of the terms in the sum are raised to the same power, k, irrespectively of the index r. We therefore have a total of k terms, each of which is equal to lambda I raised to the power of k plus lambda I raised to the power of k. We can therefore reduce 37 to the simple expression in 30a, where the sum is replaced by a factor of the form 2 times k times lambda I to the power of k. This substitution is possible because, as we have explained, this is the value that the sum takes. We can now substitute the expression in 30a back into the middle sum in 36, the one that is over indexes k associated with different filter coefficients hk. This substitution is implemented in the first equality in 39. We then reorder terms to obtain the second equality in 39. We pull the factors 2 and mi, which do not depend on the summation index, as common factors. The manipulations we started in 37 and are about to complete are the key steps in the proof of fact 1. The reason why these steps are key is that we have ended with an expression that is, first of all, unexpectedly simple, and second, suspiciously similar to the derivative of the frequency response of the filter. Indeed, remember that we can write the filter's frequency response as a series with coefficients hk on powers of lambda. Therefore, the derivative satisfies the relationship we show in 40, where lambda I times the derivative h prime of lambda I is written as the exact same series that appears in 40. This is, by the way, the same observation we made when studying dilations of the shift operator S. The two proofs are conceptually identical because of this, except, of course, that reaching the point at which this observation becomes useful is much easier in the case of dilations. Continuing with the proof, equation 40 is substituted into equation 39, where the series is replaced by the product lambda I times h prime of lambda I, these two quantities being equal because of 40. This ends the core part of the proof of fact 1. The rest is just algebra. You should realize that this is true because the quantity we highlight in red in 41 is something we can bound with the integral Lipschitz condition. The bound appears in equation 6 if you want to check it. This is possible indeed, but it has to be checked. To that end, consider the norm squared of delta 1 of S times x, its energy, if you prefer. In equation 42, the first equality comes from substituting 41 into 36. This eliminates the two innermost sums in 36 and leaves us with the outermost sum only, the one that is over GFT indexes I. In this sum, the eigenvectors Vi are orthogonal and have unit norm. Therefore, each term of the sum is the side of a right simplex. Then the theorem of Pythagoras holds, and we can write the squared norm of the sum as the sum of the squares of the individual summands. Observe now that in 42, the eigenvalues of the error matrix are all of them bounded by epsilon. This is just the definition of a norm. The norm of a matrix is its largest eigenvalue. All of the eigenvalues m sub I of the error matrix E are smallest than its largest, which is the norm epsilon. Further note that the factors lambda I times h prime of lambda I are bounded by C. This comes from the integral Lipschitz hypothesis on the frequency response of the filter, as stated in equation 6. We can therefore bound the operator norm of delta 1 of S as we show in 43, where mi squared is bounded by epsilon squared, and lambda I times h prime of lambda I squared is bounded by c squared. To complete the proof of fact 1, recall that the graph Fourier transform preserves energy. Therefore, the sum of the GFT components in 43, which is the energy of the GFT of the signal x, equals the energy of x itself, which is 1 because we are considering the computation of an operator norm. Take a square root on both sides of 43 to conclude the proof of fact 1. Notice how working with energies here instead of norms is crucial in obtaining a bound that does not depend on the number of nodes n. We could have used the triangle inequality in 42, but that would have prevented us from taking advantage of the orthogonality of the eigenvectors V sub I. We took advantage of that by working with square norms or energies and invoking Pythagoras' theorem. This observation is not crucial to understanding the proof of fact 1, but it is an interesting observation nevertheless. The observation is also significant because the same cannot be done in the proof of fact 2 we are about to see. The impossibility of invoking Pythagoras' theorem is the reason why the square root of n terms appears in fact 2. Conversely, the possibility of invoking Pythagoras' theorem in this proof is the reason why a square root of n term does not appear in fact 1.